now we're back, and this time we're going to continue our discussion about Doppler effect. Where in our first video we discussed about the different equations to determine the wavelength of the sound waves, the frequency, and also the different velocities: the velocity of the source, the velocity of the sound in the air, that is 340 meter per second, and also the velocity of the listener, and the different sound conventions that we're going to use when the source or the listener is moving in different directions. All right, now this time we're going to solve or analyze the first sample problem under the Doppler effect topic. Now, this problem is asking us to determine the wavelength of the sound wave. So the problem statement goes like this. A police siren emits a sinusoidal wave with frequency of 300 hertz, and the speed of the sound is 340 meter per second. Okay? And the first question is, we're going to find the wavelength if the siren is at rest. And letter B, if the siren is moving at 30 meter per second, find the wavelength of the waves ahead of and behind the source. Alright? So take note that what is given in the problem is the frequency of the source, that is 300 hertz, and the speed of the sound in the air, that is 340 meter per second. And what is asked what is asked here in the problem is that we're going to find the wavelength if the siren is at rest, meaning it is not moving, right? And if the siren is moving at 300 meter per second, the problem is asking us to determine the wavelength of the wave ahead of the siren, and also the wavelength of the sound wave that is behind the source or behind the police siren. All right. So, now, this is the solution. So, the Doppler effect is not involved in part A, okay? Because there is no listener here, all right? It is only, what the problem is describing is that the police siren is at rest, all right? And the problem is asking us to determine the wavelength of the sound. All right. Okay. Now, since neither the source nor the listener is moving, right? So there's no Doppler effect in this condition in letter A. Now, in part B, the source is in motion, and we must invoke the Doppler effect here. All right. So let us have the setup. So for part A, we are going to use the relationship of the velocity, okay, of the sound wave, right, with the lambda or the wavelength and the frequency of the source. Now take note that the problem is asking us to determine the wavelength of the sound. So from this equation, we are going to derive the equation for the wavelength. So the formula that we're going to use to determine the wavelength of the sound is V over F sub S. That means that we're going to divide the speed of the sound, that is 340 meter per second, with the frequency given by the police siren. Okay? So this is the formula that we're going to use when we are going to determine the wavelength of the sound in part A. Now what about in part B? In part B, the source moves with the speed v sub s. All right. Now, the equation that we're going to use are the following. All right. For the front of the police siren, the formula, okay, to determine the wavelength of the sound is v minus v sub s over f sub s. All right. This is the front, and at the back of the police siren, there is V plus V sub S over F sub S. So these are the two equations that we're going to use to determine the wavelength of the sound in different portion of the source. Right? Now, let us now execute the computation. Now, since the what is given, right, in the problem is 340 meter per second. That's the velocity of the sound, right? And the frequency given by the problem is 300 hertz. So we're going to divide the two. 340 meter per second divided by 300 hertz, and that is equal to 1.13 meters. So the wavelength of the sound, okay, when the police siren is not yet moving, okay, in all direction, is equal to 1.13 meters. Now, when the source is moving at 30 meter per second, now what will be the wavelength of the sound at the front and at the back of the police siren? So, at the front of the police siren, we're going to use this formula, as what I've said a while ago. So, the velocity of the sound in the air is 340 meter per second minus the velocity of the police siren, right? That is that is 30 meter per second. So we're going to subtract 30 meter per second to 340 meter per second. And the difference of that will be divided by 300 hertz. That is the frequency of the source. So after after the computation, so we have 1.03 meters. Okay. Now what about at the back? Okay, at the back of the source of the sound. So the equation that we're going to use is lambda equals v plus v sub s over f sub s. So we're going to add 340 meter per second plus 30 meter per second, and the sum of that will be divided by 300 hertz. So we have 1.23 meter per second. Now take note, I want you to pay attention with this, that the wavelength of the sound when it is at the front of the siren is lesser than the wavelength of the sound when it is at the back of the siren. Okay? So, this satisfies the condition that we've discussed earlier, that if, okay, that if um, the uh, the source of the sound is moving, all right, in that particular direction, okay, towards that particular direction, so the wavelength here of the sound is shorter than the wavelength of the sound at the back of the moving source.